So this is GATE 2022 Life Sciences Biochemistry section, question number 44. The dissociation constant for a receptor ligand pair is 0.25 into 10 to power minus 7 molar. The ligand was added to the solution of the receptor such that the receptor was 50% saturated at the equilibrium. Okay, assume that the receptor has one ligand binding site. The concentration of the free ligand at equilibrium in nanomolar, correct to the nearest integer, should be dash. Okay, this is one of the very repeated question, and it is very simple also. If you know the how to solve this type of question, whenever they asked about the percent saturated, if they ask questions about a receptor which is 50% or 80% or 90% saturated by the ligand. Okay, so we'll start. So they have given us the KD value. Okay, so this is a so they have given the dissociation constant, which is denoted as KD. Okay, we are all familiar with this term KD, dissociation constant, and the value is 0.25 into 10 to power minus 7 molar. Okay, so so many of this question they asked about this percent saturation of these different receptor. Okay, so here they are given us 50% saturation, 50% the receptor is saturated. Okay, so this term percent saturated receptor, we will call it as theta. Okay, so this theta is the percent saturated receptor, and it can be given by suppose we have a receptor R and we have a ligand. Okay, we have receptor R and we have a ligand. So if ligand is bound to the receptor, it will give us, at equilibrium it will give us RL. So this is the bound form. So percent saturated receptor theta is given by concentration of this bound receptor by the ligand upon the total receptors. Okay, so this receptor could be upon any protein. Okay, so the total protein, so this R could be a protein. Okay, R could be any protein which has only one receptor. Okay, so it can have many receptors, but here they have given that assume the receptor has one ligand binding site. Okay, so that receptor will have only one binding site where the ligand will come and bind. Okay, so in case of hemoglobin there are 4 binding sites, right? 1, 2, 3 and 4. So in this case of protein, the receptor has only one binding site. Okay, so we can assume this R to be directly a protein. Okay, so the reaction will be protein plus ligand will give us protein and ligand in the bound form. Okay, so we can rewrite this as ligand bound to the protein upon total protein which is present. Okay, this is the total protein, right? Okay, so this we have to keep this in mind. Okay, now we have to find out the concentration of free ligand. We have to find out this L, the concentration of L. We have to find out the concentration of L. Okay, and we already have a theta. So what is theta? theta is 50% of the saturated protein with the ligand. Okay, so the theta value is 0.5. So we have the theta value and we need to calculate the concentration of ligand. So how to do that? We have to derive a equation. Okay, it's very simple. So we have a protein. I'll write again. We have a protein. So this is the total protein, right? So we have a protein and we have a ligand. Okay, so we have a Kd at equilibrium. What will happen? So when this protein and ligand will dissociate to give a total protein and ligand, this is in the bound form and this is in free form, right? And the constant dissociation constant Kd for this will be, it will be what? Product upon reactant. So this will be total protein, reactants upon bound protein. Okay, this is very simple. This is total protein concentration, this is ligand concentration, product of reactant upon the product of products upon reactants. Very simple, dissociation constant. Okay. And we already know that the total protein can be also calculated. The total protein is also equal to free protein plus the protein which is occupied, that is occupied by ligand, right? Occupied by ligand. We can also call this as bound, right? Very simple. So the total protein will be always be equal to free plus bound. Very simple. So the total protein PT concentration will always be equal to free protein. Let's write F here. This F means free protein plus bound form of protein to a ligand, which is this PL form. This is the bound form of protein. Okay, so okay, this will be the free protein, not the total protein. So this is F. So this won't be total protein, but this will be free protein. So when bound protein, it will dissociate to give us free protein plus ligand concentration, and the Kd will be free protein into ligand upon bound. Okay, and from here we can find out that free protein is equal to total protein minus bound. Okay, and if we plug in the values here, the Kd will be equal to total protein concentration minus bound into ligand upon okay. So let's, if we cross multiply this, we'll get whole into ligand, right? So if we multiply this inside, we'll have this will become total protein into ligand concentration minus bound protein into ligand concentration. You from so we can so the total bound protein, the term is here also, so we'll take this here. So this will become Kd bound to ligand plus bound ligand into ligand concentration, and this will be okay. So we can take this common, and we'll have Kd plus L, okay, and we'll have total protein. Okay, this L can come here, right? So next what we can do is we can take this term on this side. So total protein upon bound form of protein is equal to Kd plus L upon L, okay, ligand concentration. But we already know what is this. This is, so we already, I told you that theta, that is percent bound, is bound, it's a fraction of bound protein to the total protein, right? So this term, this will become 1 by theta. So the theta will be equal to ligand concentration upon Kd plus ligand concentration. Okay, we can derive this, or you can simply keep this in mind. So this is, as I mentioned in the previous slide, percent saturated ligand, which is equal to bound, fraction of bound ligand to the total protein, right? This is the fraction. Percent saturation, like percent bound ligand, or you can simply keep this in mind, okay? This theta, this is fraction percent saturated ligand, is equal to ligand concentration upon Kd by Kd plus ligand concentration, okay? I can explain again. So theta, we all know, it is bound form of protein to ligand upon protein, total protein, right? This is percent saturated sites on the protein, percent saturated sites on protein, right? This is the term theta. So the total protein, we can write the total protein as free plus bound, right? The free protein, we can write a prefix F, and the bound will be bound to a ligand. So this, we have this term, okay? So the free protein, so you know it is very difficult to find out the concentration of free protein. So suppose I give you a ligand, any ligand, so I give you a growth factor, okay? In a I give you a proper pure growth factor to you, and I tell you there are cells which have growth factor receptor to them, okay? And I told you to mix those solution. So the growth factor will go, and bind to the receptor on the cell, right? It will go and bind to the receptor on the cell, and this, the only bound form you may be able to measure, because they are secreting, after binding to the growth factor, they are secreting some molecule, and you can easily measure that molecule, right? You can easily measure the molecule. So the bound form, it is, we are able to measure the bound form. We already know the total protein. So I give you, suppose 10 million cells, okay? I give you 10 million cells, and in general one cell has approximately, we can say it has approximately 10 to power 13 receptors, okay? So we can easily calculate the total binding, total receptors, right? We can easily calculate the total receptors, we can easily calculate the bound form, but it will be very difficult for us to calculate the free form of these receptor, okay? So inside the cell we may not able to know how to calculate this free form of the protein. So what we can do, we know already what is the total receptor count. We know how much is the bound by measuring some the end product of this growth factor, the signaling pathway, and we can just do a subtraction by that. So total minus bound. So this free form of protein is very difficult to measure, that's why we have to substitute this. And we can calculate KD. KD is equal to, so this free form of protein plus, okay, so the so the bound form of protein, this is a dissociation constant. So this receptor bound protein will dissociate us and give us free form of protein or receptor plus ligand, right? And the KD is equal to the product of these two upon PL, this. And as I said, this is very difficult to calculate the free form of the receptor bound by the ligand, so we can use this term. So this we are just replacing here, and then I just solve this for the KD to get everything in terms of ligand. And what I got, that theta is equal to, finally we need to equate it to theta. What I got, theta is equal to ligand upon KD plus ligand concentration. So we already know what is theta. Yeah, so the KD we already know, theta we already know. We need to find out free ligand at equilibrium. So theta is 0.5, 50%. KD is 0.25 into 10 to the power minus 7. So we'll put it in the formula. Theta is equal to L upon KD plus L. 0.5 into 0.25 into 10 to the power minus 7 plus L is equal to L. So this will become plus 0.5 ligand is equal to ligand. We'll take the ligand term to the one side. So this will become 0.5 ligand. This is ligand will so ligand minus 1 of ligand minus 0.5 ligand will become 0.5 ligand. So ligand concentration will be 0.125 upon 0.5 molar, right? Which is 0.25 molar into 10 to the power minus 7. Let's not forget 10 to the power minus 7. Okay, here we'll also have 10 to the power minus 7 molar. And if we so if we add if we want to convert into nanomolar, it will become 25 nanomolar, right? This conversion is correct. Nano is 10 to the power minus 9. So if we add 2 more zeros, it will become 25 nanomolar. Everybody got? Yeah, so the answer is, in nanomolar we'll get 25. So the ligand concentration is, free ligand concentration is how much? 25. Okay.